Hello students, and welcome to this video where we're going to discuss the concept of derivatives and slope of a graph. I'm going to warn you now that there is a lot of text on these slides, and as always when you're watching a video, it's my expectation that you probably want to be either following along in your notes or taking notes as needed. So it'd probably be most helpful to you if you pause and play this video kind of after you've written things down, because again, there's a lot of definitions and a lot of text. But we're going to start out by talking about what exactly is a tangent line. So in geometry, a line is tangent to a circle when the line intersects the circle at only one point. So if I were to have a circle, and I'm drawing on here so it may not look very great, but if I have this circle here and then I want to create a tangent line, I am getting one point on that circle and then my line is going through that one point. So it is touching the circle only at that individual point. The key word here being the number 1. So a tangent line is a line that touches a curve at a point that best approaches the slope of the graph. So in the past in geometry, you've always looked at this in reference to a circle, but our goal today is really going to take this beyond. We want to start looking at individual functions. So if I imagine having, something that resembles a quadratic function or maybe some, random graph, or like an exponential function. The idea here is I want to identify a point and draw a line through it, any point on that graph, and that is representing my tangent line. And if I can find the slope of that line, then it is going to best tell me about the slope of the entire graph. Unfortunately, there are some flaws regarding this, because if you look at my very first example, if I draw a line here on the left versus drawing on the right, one of those has a positive slope and the other has a negative slope, right? And so if I only draw one line and I want to make some approximations or make some conclusions about the graph as a whole, then those aren't going to be very true approximations. And so we get to this idea or this concept that the more and more lines that I can create, the better approximations that I can get. So what is a tangent line? Well, we know that for a straight line, the slope is the same at every point on the graph. The slope of the tangent line for a general graph tells us how the graph changes from point to point. So the second takeaway is what is a secant line. So a secant line is very similar to a tangent line, however the key word being 2 points. So the use of 2 points is the secant line. It is a line that runs through the tangent line point P plus an additional point. As the slope of the secant line approaches the slope of the tangent line, a limiting position is going to exist. I have put this into quotations because I want you to think about that idea, a limiting position. And we learned about limits already. And so there is going to be a relationship between this concept of limits with the secant line. So this means that the slope of the tangent line is said to be the limit of the slope of the secant line. So again, just to give you a visual representation, if I had a graph like this, that's a terrible looking graph, I apologize, and then I make another graph. If I'm talking about the tangent line, I'm just going to grab 1 point and create my line. If I'm talking about my secant line, I'm going to create 2 points and I'm going to draw a line through them. Okay? All right, so let's actually see how we're going to utilize this. So approximating the slope of a graph, I have the function f of x is equal to x squared, and I want to approximate at the point 1, 1. So we're going to identify point P to be the point 1, 1. Now, I want you to keep in mind what it is that you're trying to do. You are trying to approximate the slope. And if you recall from previous lessons, we know that when we want to look for the slope, we have our slope formula, which says y2 minus y1 over x2 minus x1. This requires me to have an x1, y1 coordinate point and an x2, y2 coordinate point. So I need 2 separate points. And as of right now, given information, I have 1 point, 1, 1. So I need to go and find a point Q. And the way I'm going to find that is I'm going to pick an x value. So I'll pick 2. And then I'm actually going to solve for my y value based off of my function that I have, x squared. So I'm going to take 2 squared. 2 squared is 4. So that's how I'm not just choosing some random numbers. I'm actually solving to get a respective point that would be on that function. Okay, so with that being said, now I have 2 points, so I can solve using my slope formula. Y2 minus y1 over x2 minus x1, and I can solve, and that gives me a slope of 3. So this is all that this is an approximation. It is a pretty good estimate of what my slope could be. But now let's dig a little deeper and use this idea that we're looking at a limiting position. And so if we're going to look at a limiting position, I want to find my slope. So I'm going to use my P equals 1 point. But I'm going to solve it using different Q points. And I'm going to try this a couple of different ways. So 1.001 gets me a respective y of 1.002. Oh, I'm so sorry. And then I'm going to try another Q point. I'll do the point 1.01, and that gets me a respective value 1.02. And then I'll try another Q, and that will be 0.99, and that gets me a respective y value of 0.98. And so what you notice is my x values, I'm trying to revolve them around the number 1. That way, you know, I'm getting a better idea of kind of what's happening as I get closer and closer and closer to the actual value of number 1. And so now I'm going to plug into my slope formula. I'm going to have to do it 3 different times using each individual Q and then the P value. And when I actually solve and find my slope from this Q, I end up getting that m is equal to 2. From this Q, I end up getting that m is equal to 2. And from this Q, I get that m is equal to 2. So although when I solved it using whole number values, I got 3, as I thought about my limiting values, my limiting positions as I got closer and closer to 1, I actually end up getting that the slope is equal to 2. So that's an even stronger approximation of the slope of a graph. So the definition of a tangent line with a slope m. So if f is defined on an open interval containing x, and if the limit as delta x approaches 0 of delta y over delta x. So keep in mind that when I think about delta, delta just means the changes. So I'm looking at the changes in y's over the changes in x, which again, if you go back to our slope formula, y2 minus y1 over x2 minus x1, that is the same thing as saying m is equal to the changes in y's over the changes in x. So I'm sitting here and I'm saying the limit of my slope formula, and that this is equal to, another way to write this is the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x exists, then the line passing through some x and its respective y value with slope m is the tangent line to the graph. And so what I want you to notice, and I'm going to try to see, let me try pink. This part right here that I am circling should hopefully look familiar to you. This is the difference quotient that we've already learned. So I had mentioned before a relationship between slope and secant line, tangent line, and difference quotient. And now you're starting to see that all come together. Using the limit with the difference quotient is going to help us to be able to find the slope. So we have an example here, and we want to find the slope of the graph f of x is equal to 2x minus 3 at the point 2, 1. So before you even begin doing this, because we're actually going to use the definition of slope, which is utilizing our limit to solve this, But because I've given you a linear function, I'm more so asking you what is the slope before you even solve this, and then let's see if that checks out. And so you should be able to look at this and you know that your slope is going to be the value 2 because mx plus b, m represents the slope, and 2 is in the slope place. So I know that when I solve this, I should end up with a slope of 2, but we're actually going to go and solve this out and see if that's what we come up with. So my slope is equal to the limit, and again, I'm using the definition of slope, so the limit of delta x as it approaches 0 of f of my x plus delta x minus f of x all over delta x. Now, when I taught you the difference quotient, instead of delta x, I used h. Feel free to replace every delta x with h here. You do not have to use the delta x, okay? So just kind of keep that in mind. So now I'm going to actually solve this. So I'm going to go off to the side. I'm going to do this in different colors. I first need to find, and I'm going to replace this with x plus h because it is easier to think about that way. So I'm doing this first part right here, the f of x plus delta x, and I'm writing it as f of x plus h. And I'm going to solve that. So how am I getting this? Well, I'm using my formula, my function, 2x minus 3. And for every x I see, I'm plugging in x plus h. And I'm going to simplify. And there's nothing else that I can do. So then I can go over here to my formula. And I can say, all right, I have the limit as, and I'm going to write as h approaches 0 because I don't want to use the delta x's. Of 2x plus 2h minus 3 minus my entire function, which is 2x minus 3, all over h. And I'm going to simplify that again. So limit as h approaches 0 of 2x plus 2h minus 3 minus 2x plus 3 all over h. And I'm going to see what things cancel out. And so my 2x and 2x go away. My minus 3 and my plus 3 go away. And now all I have is my 2h over my h. And so the h and the h cancel each other out because it's just a monomial term. So I am left with the limit as h approaches 0 of 2. And we've learned a limit property that says anytime you are finding the limit of a constant term, it is just equal to 2. And so now that I have gotten the value of my slope, I am all done. And what you normally would do is if you were trying to find it at a particular point, sometimes when you end up at your m, you would end up with an equation. So you may have some x's in there, and you would actually plug in this point 2, 1. So you'd plug it in order to find like the equation of your line. But in this case, you're just finding the slope. We don't have any type of function, so we're good to go, and we're able to stop there. Okay? All right, so moving on to the definition of a derivative function. So the derivative of x is given by f prime of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x, provided that the limit exists. Now, this should look familiar to you. It's exactly what we had up here a second ago, right? When I had my definition, the limit as delta x approaches 0 of my difference quotient. That's the same thing I have here. So now you're seeing a relationship between slope and derivative. They're the exact same thing. So some vocab, a function is differentiable at x when its derivative exists at x. So there's some words. There's this word differentiable. We have the word derivative. So a function is, if it has a derivative, then the function is differentiable. And the process is called differentiation. So I'm looking for the derivative. If I find it, then the function is differentiable. And that entire process is called differentiation. So I want to make sure you're familiar with those words as you begin to hear those. And there's actually some different notations for derivatives. So we have this f prime of x. It looks like an apostrophe symbol. We have d over dx of my f of x function. I have this capital sub dx of y. And then I have a y prime. And then I can have dy over dx. And I've made them into columns like this because I want you to see that these kind of have a relationship. Like f of x is the same thing as saying y. So the top one is the more formal way to write, you know, that you're dealing with your function's derivative, whereas the bottom one is the more informal way. In the second column, I generally use the dy over dx. You know, f of x represents y, and so that's just moving, you know, the f of x along with the d. So d f of x is the same thing as saying your d of y. So both are used. Not one is better than the other, but one's just kind of more commonly seen as being more formal, and that would be the bottom one in this case. And then this last column, I have provided that to you because you sometimes see that as you look in upper level math textbooks and maybe some articles if you're reading, but honestly, I don't really use that in this class, and I don't think you'll come across it too often. All right, so find the derivative of f of x is equal to x cubed plus 2x. So this is a pretty lengthy problem. I encourage you to pause this video and to go ahead and try to solve this on your own using the definition of derivative. Keep in mind that your definition is f prime of x, so the derivative of f is equal to the limit as delta x approaches 0 of your difference quotient, which is x plus delta x minus f of x all over delta x. And again, feel free to change your delta x's to h's if you'd like. I encourage you to solve this problem. Once you're done, feel free to resume the video. All right, so looking at this problem, I'm going to first want to go and solve. I am going to look for my f of x plus h, and that's going to be a little challenging because I have x plus h all cubed plus 2 times x plus h. You're going to want to start out by probably squaring your x plus h and then going ahead and multiplying that by the additional x plus h and then simplifying that on out. I'm going to go ahead and do this math for you. So you should end up with x cubed plus 2x squared h plus xh squared plus x squared h plus 2x h squared plus h cubed plus 2x plus 2h. I'm just looking to make sure everything looks right. And it does, okay? And then we have our minus our f of x function, which is x cubed plus 2x, so both signs are going to change. So if I go ahead and write that on out, I have the limit as h approaches 0 of my x cubed plus 2x squared, and let me not use yellow, that's not a very good color to use right now, x cubed plus 2x squared h plus xh squared plus x squared h plus 2x h squared plus h cubed plus 2x plus 2h, and then minus my f of x, so that's minus x cubed minus 2x all over an h. And let's see, if I go and simplify this, my x cubed goes away with my x cubed, my plus 2x goes away with my minus 2x. I have like term here and here. I have another like term here and here. Let's see, do I have any others? I think that's it. So this gives me the limit as h approaches 0 of 3x squared h plus 3x h squared plus h cubed plus my 2h all over h. And if I simplify that again, the limit as h approaches 0, and I'm going to take out my h, that's 3x squared plus 3xh plus h squared plus 2 all over h, so that my h's can cancel out. Whew, this is a lot. and I'm left with my limit of my function. And now, because I'm looking for my derivative, I'm going to actually find the derivative of h approaching 0. So all of my h's, I'm going to plug in 0. So that's going to be 3x squared plus 3x times 0 plus 0 squared plus 2. And that ends up giving me 3x squared plus 2. And this represents the derivative. And I believe those were the directions were to find the derivative. Am I correct? Yes, those were the directions. So that is your derivative right here. So this would be your f prime of x. So a lot of work because you had to cube that function. Again, you know, I didn't really show you the work because it's my expectation that you're pausing the video and doing the work on your own and just confirming that you get the same thing. But yeah, I hope you found this helpful for you. So as always, if you have any questions or concerns, please don't hesitate to reach out and ask. I'd be happy to help. Otherwise, have a wonderful rest of your day.